So let's take a look at writing different kinds of equations for these double replacement reactions that can happen in solutions. We're going to look at writing molecular equations, the kind we've already been using, complete ionic equations, and net ionic equations. One reason these many types of equations are written is this can actually be a way to figure out if a reaction is truly going to happen or if you're simply going to get a mixture of the same ions that you had present in the original solution. So what we're trying to do is find a paper way to figure out if it's a real reaction or not. Here we have clear colorless sodium hydroxide solution and blue clear copper nitrate solution. When they're mixed together, we definitely get a reaction. Do you see the different colored blue cloudiness? That's a precipitate. That means one of the new substances that's formed is insoluble in water, has new properties. So this is a molecular equation, complete and balanced for this particular reaction. First, we did a double switch. We bonded sodium to nitrate in the correct proportions, and then copper plus 2 ions to hydroxide in the correct proportions. And then I used a solubility chart to look up and see which of those two products must have been the blue solid. I kind of already thought it would be the copper compound because transition metal compounds are often highly colored. And when I look on a solubility chart, that's just what I find out. Now let's take that complete molecular equation and write it as what's called a complete ionic equation. This means we're going to take all water-soluble ionic compounds apart into their dissociated ions, and we're going to carry those coefficients along with them and make sure to write charge. So from sodium hydroxide, we get sodium and hydroxide ions. From copper 2 nitrate, we get copper 2 ions and nitrate ions. Note that as each compound dissociates into its ions, the coefficient comes right along. So from 2 sodium hydroxide formula units, we're going to get 2 sodium ions and 2 hydroxide ions. From 1 copper 2 nitrate formula unit, we're going to get 1 copper 2 plus ion and 2 separate nitrate ions. This shows that the initial materials were all dissociated ionic compounds in solution. What we need to do next is do the same thing to the products. But remember, only soluble ionic compounds come apart into their ions. So take a look at the products and think what it's going to look like when we dissociate into ions. For the sodium nitrate, we're going to get sodium ions and nitrate ions. In fact, we'll get 2 sodium ions and 2 nitrate ions. And copper 2 hydroxide, notice, is solid. It does not dissociate, and so it stays together as an intact formula unit. This is called a complete ionic equation, where all water-soluble ionic compounds are dissociated into their ions, and all insoluble compounds are left as either molecules or formula units. Now we're going to turn it into the useful form, which is called a net ionic equation. In this form, we show only the ions and compounds that are directly involved in the change. We remove what are called the spectator ions. If we look at the complete ionic equation, we can see that there are 2 sodium ions on each side. There's also 2 nitrate ions on each side. That makes those spectator ions. They're there in the beginning and they're still there just as they were in the end. They can be crossed out, leaving only the ions and formula units that were directly involved in chemical change. That leaves us with what's called the net ionic equation. 2 hydroxide ions react with 1 copper 2 ion to make the solid copper hydroxide or copper 2 hydroxide. This represents only the ions that were involved in the change. It shows, since there are still formulas left in the equation, this shows us that this was a true chemical reaction. Let's try another. This time we have sodium chloride in a clear colorless solution, and we have copper 2 nitrate in a clear blue solution. Will this be a real reaction or not? Well, let's do it on paper by using molecular, complete ionic, and net ionic equations and see what we would predict for this particular possible reaction. So we need to start writing an equation for this. First, let's start with a molecular equation. NaCl plus CuNO3 sub 2 will make NaNO3 and CuCl2. We need coefficients to balance. Everything's written as an intact molecule. If we look up the two products, we find out that neither of them is insoluble in water. In other words, both would be AQ. That means that we can write the molecular equation as shown partway down the slide. Let's take it further and write a complete ionic equation. Remember, this means that we take everything that's water soluble and dissociate into its existing ions. So we're going to get 2 sodium ions and 2 chloride ions, and 1 copper plus 2 ion and 2 nitrate ions in the reactants. What will we get in the product? So look at the formulas or formula units for the products and take anything that's water soluble apart into its separated ions. Do you see that we're going to get 2 sodium ions and 2 nitrate ions and 1 copper plus 2 ion and 2 chloride ions? That then gives us our complete ionic equation where everything water soluble is shown as dissociated ions. Now you might notice something kind of interesting about this particular complete ionic equation. Everything is ions. Start looking for those spectator ions, the ions that are there in the beginning and still there, exactly the same as product. We can cross out the sodium ions and we can cross out the chloride ions. We can cross out the copper plus 2 ions and we can cross out the nitrate ions. Wait a minute, that means there's absolutely nothing left. We had a bunch of ions in the initial solution when the two were combined. We have that same bunch of ions in the final solution after the possible reaction took place. That means there's no reaction. There was no new material with new properties formed. All we have is the exact same mix of dissociated ions that we had to start with. There is no net ionic equation. This means in this case there was absolutely no reaction. Which is why, when we mix the two together, what we actually see is simply a diluted blue. We've taken a blue, clear solution and mixed it with a clear, colorless solution. That dilutes the overall color, but we have the exact same ions dissociated in all cases. The easiest way to write this is NR. So how do you write molecular, ionic, and net ionic equations? First, you do have to get to a molecular equation. This means you write the reactants, the best predicted products, you balance it, and everything is shown as an intact compound. That's called a molecular or formula unit equation. Then you dissociate all strong electrolytes into ions. These would be all the water-soluble ionic compounds. Also, it would be acids, strong acids and strong bases, but we haven't done that. That creates a complete ionic equation. Then you cross out anything that remains unchanged from the left side to the right side, the spectator ions. These are removed and you're left with either nothing, which means no reaction, or a net ionic equation showing the ions and formula units involved in the actual chemical chain.